We have James yet again, together with Joshua Allen. As I said, I didn't get to do a proper introduction of James before, but are you ready from these combination of two talks? You might be wondering, is James a statistician? Is he a computer scientist? Is he an engineer and developer? Actually, his PhD is in political science, and he's an expert in all of these things. And we have been delighted to have him as the now Chief Privacy Engineer on the Privacy Tools Project and OpenDP. And we are also delighted to have Joshua Allen, a Principal Data Scientist at Microsoft, as one of our key collaborators on the system building that we've been doing. And they are going to talk to us about system integrations.
Yeah, I'm delighted to continue to bring these two talks together, and to have bring Joshua on board and talk about the work that we've been able to do with him, which has just been some of the most fundamentally interesting work that I've gotten to be able to work on in my career. You know, my daughter was born when I first started working on differential privacy, so I get to remember how old she is by reflecting on when I first started working on this. And you know, now that she's 6, Joshua and I, you know, and all of the people, my colleagues at Microsoft and here at Harvard, you know, have released this thing that sort of has been gestating for 6 years in different prototype stages. It's really great to see an end-to-end use case built for differential privacy. And you know, that excitement is not to say to this audience, look at everything we've done. It's the goal of describing that is to say, you know, it was 4 or 5 years of work here at Harvard when we were working by ourselves, trying to build things ourselves and trying to build everything ourselves and trying to build end-to-end solutions ourselves. And when you start to have collaborators who can chip in other components that you trust just as well as the ones you know yourself, the things just accelerate so much faster. And I think that's the underlying story of OpenDP, is that there should be a really broad set of underlying components that we can all trust, each written by their own experts, and the explosion of growth and the things that we'll be able to build that we've been imagining for so long will finally come to fruition. So I'm going to encourage Joshua to talk over me at every opportunity he can, because he has a better perspective on a lot of this. You've already seen this graph before, which is how we imagine the OpenDP commons being used by end-to-end systems. We expect, you know, that different people will be building end-to-end solutions that need differential privacy for a variety of use cases. And they're going to have enough things that are interesting about or unique or tailored to their own research agenda that they live in their own blocks. We call them system 1, system 2, system whatever. System 1 is this joint project I'm talking about for a curator for releasing statistical analyses on data in a cloud environment. This joint project with Microsoft. And system 2 is hopefully your program. And system 3 is the other person. And there's 200 participants today, so hopefully we'll get at least 20 systems by the end of the day. But the question is, how do we build a commons so that there is this ability to lean on each other and reutilize these underlying components? Michael talked about the library desiderata as being these 8 elements. These are the things the library ought to be able to do in order for everybody to be able to contribute and use the library. And all of these things translate into system building principles themselves. That is the idea that things should be scalable and they should be extensible to different conceptions of privacy, and they should be flexible, and programmability is key. All of these turn into system, become inherited principles of the system itself, but they lead to questions about how it is that we should build systems and how it is that we should build objects that live in the commons so that everybody can use them, and so it does scale properly, and so that everybody's definition of privacy loss is validated. Okay, so these, I think, are 5 of the underlying core questions that are addressed in the white paper. First of all, what kinds of stores are we getting data out of? Because the commons is going to need to be able to read and write from stores or ship code to where the data is stored in trusted ways. How do we deal with identity and authentication and authorization? And those are nuanced concepts that are similar to each other, but not exactly the same. So that we know that if we build an end-to-end system, the vulnerability is not that people can hack into it. What are the use cases for distributed computation? You know, I've always generally worked with data that's in memory or, you know, data that's local. How do we, it's been fascinating to see, the application in this system that Joshua can describe more for distributed data, for sharded data, for computation with distributed workers. And I think there's research questions there in all these pragmatics. How does differential privacy work when it's divided across workers, some of whom might fail? What are the limitations that the languages choices that we're proposing impose on different system designs? And this is a really important question that I hope can be fleshed out. We have a language choice proposal for Rust because of some of its benefits, but what are the potential drawbacks? Maybe there need to be multiple runtimes from one reference. And then similarly, if we're going to use that library, how do we build an API so that it works for every possible system? And so that there's only, so there's one key API to get into that library. How do we achieve language neutrality? Is this an unopinionated API, or do we need to build different opinionated ones? Okay, so I'm going to talk a bit, since I don't have answers to these questions, but I think they need to be fleshed out in this discussion. I'm going to focus a little bit on talking about the one system that we have, the most experience with, which is this joint project with Microsoft. Obviously, there's not an OpenDP library for this to integrate with, but what we did was we built a prototype library because we needed something. So I'll talk a little bit about our experience building a prototype library, which is not the OpenDP library, but hopefully some of the code can be reused. We would expect that a library that comes out of this community and reflects more of the ideas that Marco and Michael were proving, can integrate with our system too in the future. But some of the experience of using just a default prototype DP library have informed some of the system choices we think are necessary, okay? And this system's, it's pluggable, it's built into modular building blocks. We hope multiple of these building blocks, when they're mature, could go into the DP Commons. Everything here is open source. It is joint with Microsoft. Microsoft, I won't speak for Joshua, but I understand, will be used as a product. But at the same time,
this is Joshua.
Adoption for others.
Yeah, I'll just jump in a little bit here.
Yeah,
one of our goals with this,
lost your video.
We've been, we've been deploying differential privacy, internally for internal scenarios for about 7 years now. But we have a wide variety of systems. So we have some things that run on Scala and Spark. We have internal custom data processing system called Cosmos. We use SGX and so on. And a lot of these are one-off systems. And so one of our goals when we heard about this project was, to try to test out some of these prototype libraries that are being considered and see to what extent we could start using something that was open source and start to replace some of our internal code. And there's a lot of things that we do internally that we think of as sort of defense in depth that are, things that we don't even necessarily do a lot of PR about, but, we like to make sure that we're using differential privacy. And so that was one of the areas where, where we focused at first was, can we use these libraries to target a variety of the internal backend data storage engines that we use, and replace some of our scenarios. And at the same time, of course, we have, we're a very large platform provider. And so we have a lot of customers that, come to us with requests, and, they may also, some of them may use Postgres, they may use SQL Server, they might use these different platforms. And so, we looked at this as both a co-development and an evaluation exercise.
So this is mostly here to answer questions in the future, but there's, there's a fairly detailed architecture here with a large number of components. Not all of these, are up and running yet, but let me talk about the heart of the system, which is 6 components that have been fleshed out pretty strongly, and which inform what we think, the OpenDP Commons would need. There's this underlying library, which is a prototype library of differentially private algorithms written in Rust, has a large number of end-to-end algorithms, but really broken down into individual components and utilities. There's an API that uses an analysis graph, and I'll talk about that more in the future. There's a toolkit, an SDK, so that you can execute this stuff against different types of stores, CSV, flat files, or Postgres, or SQL databases. There's this API to run things in SQL that looks a little bit more native. And then there's two forms of validation. One static validator, which looks a little bit like, is a step towards the direction that Marco and Mike are trying to push us, which is reason about code that's been constructed from components to prove its differential privacy ahead of time, but not as capable as they want to generate. And then a stochastic validator, which is actually mirrors some of the stuff we heard in the Google talk, which is trying to find edge cases which are not differentially private. As a form of unit testing. So let me talk about some of these pieces, or actually this might be a good time. Josh, are there things in here that sort of you want to expand on that talk about, as you were saying, the integration across all the different types of services that you need in your own use case?
No, I think from this one, I would just highlight, I would, I guess, reemphasize what Miguel's presentation said and what Ilya's presentation said, that, we don't want to boil the ocean. And, with any large, enterprise deployment, there might be a lot of like super specialized edge cases with, some really, bleeding edge research that probably won't see the light of day for a while. But then there's this huge low-hanging fruit of these, analytics type scenarios, some of these machine learning scenarios where, it's actually not difficult to add differential privacy. And there's, potentially a lot of exposed risks, because these, within these big data collectors in the Fortune 500, you're looking at the vast majority of the world's private information is being collected, and there isn't a ton of awareness about the risks that are out there, and so rather than people going off and focusing on all these science projects at the fringes, there is a lot of room to focus on these low-hanging fruit areas as well. And so that's where we felt that a lot of the focus of this analysis graph that supports these data science scenarios is is just a big thing. Some really basic SQL scenarios, even maybe less than some of the join stuff that, the Google guys have built, is already, a big value add that people could use. Yeah. And so, yeah.
So the question came up, why Rust as for this prototype library, and why did that translate into a recommendation? Originally we talked to lots of people and systems builders, and C++ was fairly popular, as a way, because it's very easy to build bindings into other languages. So, that allows for easy adoption, and also it's, it's performant, C++. So again, the catchphrase that I would promote would be that Rust is C++, only it's fixed, which is to say it's first of all, it's a functional language, but it's an imperative functional language. So it doesn't have all, it's not a Haskell where things are super rigid. It's in the imperative direction, but being functional does make it easier to reason about. But what really makes it more easy to reason about is all the memory safety that's built into it. Okay, so you have, everything is immutable by default. You have really good memory safety. There's a really good ownership model of, which, in the scoping, what is owned by what and what can address which memory performances. You basically rule out all of the problems of dangling pointers, memory erases, all those kinds of things that make it impossible to reason concretely about what's going to happen when you start addressing memory in C++. And when we were looking through all this, we ourselves stumbled across some Microsoft releases from their security teams that had said they estimated that 70% of the patches they were releasing were memory issues that would have been solved if they weren't using C++, but were instead using Rust. And so there is a lift here, which is we'll talk about this, which is it's another language for developers or contributors to learn. I would say from experience, it's if you've picked up one or two languages already, it's going to be very, very similar. Also, For those who can't make that lift, I'll talk about bindings and how you can execute the Rust code or contribute to the underlying core through other languages like Python, like R, and how that needs to be part of the workflow in order to build a community of people who can contribute. Okay, but basically the reason for Rust is the advantages of a functional language and the advantages of memory safety make it very, very easy to reason about. But at the performance level, it acts with the performance of C++, and it inherits all the binding features of C++. So it's very interoperable, okay? So this is a strong proposal that came out of the white paper, which is the library, the core library, should be ported OpenDP. That doesn't mean people are contributing in OpenDP, and I'll talk about APIs, okay? So in order to be able to use this system, again, we want to, there are a large number of system components in the end-to-end solution that want to access the library. So we have this API. The API is written in protocol buffers, which is not on the slide apparently. And I'll talk about that in a second. But what's fundamentally important is that the API is a way of defining a computational graph that says, much like a plan in Xelo or in some of the other privacy preserving systems, here are the things I'm going to call in the library in this sequence. And here is how outputs from one call are going to interleave into inputs from another call. So representing that component structure through the API is all that's needed to run the underlying code. And then when you have that API, you can write simple bindings into other languages. So we wrote one into Python, and it's very simple to use, and you can execute the library natively in a Python notebook. And everything can be, the bindings can be put up on, have been for this system, put up on PyPy and pip installable, so very easy to access. It looks like native. So this is an example of calling the underlying library through Python using the bindings. It just looks like Python code. And similarly, we're doing the same thing with R. You can throw it into a notebook and it executes just like like it was native Python in a Python notebook. So people who are used to interacting with the system in that way can do that. People who want to sandbox or test bed or write their algorithms this way can add Python code, get it to work with the library, and then maybe send us the Python code and think about who can do the porting into the Rust, okay? The API itself, I think, is also an important thing to talk about and to discuss in this breakout group. We built an API out of protocol buffers. It's a very popular choice for API, but if you've not seen it before, think of it as another data, serialized data language. So it's like JSON, it's like XML, anything else you might build an API in, except it's very, very heavily typed and very, very compact. Okay, so the heavy typing is really nice here for reliability and for preventing any possible side channels. You can only specify things that exist in the API. Again, Rust has exactly the same foreign function FFI, foreign function interfaces as C++. So, the bindings from Rust to protocol buffer look exactly like the bindings from C++ into protocol buffers. And then, we're providing from the API very easy bindings into Python and so on. It also, in theory, allows us to call things that are not in the underlying library if we trust them enough. And so another thing to think about with system integrations is how we trust other things. I was going to talk a little bit more about the API, unless this is a good time. Joshua, do you want to talk about either the underlying library or sort of some of these choices we made?
I'll just answer one question from the audience. So Damien is asking, if Microsoft has been using DP internally, what made us start from scratch? And I think, one of the things using the software internally is it's just written in a wide variety of languages. So it's not like there's one existing internal implementation that would be ported over. And it's, some, like our first implementations were all local model. We have some, a variety of implementations of local model. But as I mentioned before, I think that a lot of the opportunity, especially outside of the biggest data collectors, a lot of the opportunity is in the global model of differential privacy. And it's an area that's probably, better understood and more mature, and more suitable for tooling. And the other thing that we looked at was, of course, we would like to use this on some of our internal things. So, if we want to say integrate this with some of our internal database engines, what are our choices there. But we also want things that the external developer community likes to work with or works with. And so that, I think that influenced the stack ranking to some degree. The other thing that I'll point out is that we focused right now on scenarios where the analyst is considered to be trusted. So the analyst is considered to have access to the private data. This is central model, right? So the people collecting the data have access to the data. But you can imagine scenarios where the analyst is considered to be an adversary. And so the analyst has to do eyes off processing. And in fact, this is something that, I know Microsoft has systems that do this, Facebook and Google and so on, where, they'll collect data into some sort of like super secure eyes off environment. And then, the analyses that run have to, go over some kind of security boundary. And so, we're thinking ahead that we want to, use this more in those types of scenarios. And then in those scenarios, your threat model obviously becomes, a little bit more rigorous. And then you need to worry more about things like memory safety and so on. So I'm just highlighting, like, we're not claiming that, this thing, is heavily fuzzed or can be used in like a super adversarial environment, but we believe that using Rust does help, prepare for that.
And that's also where some of the features proposed by Marco and Mike are really going to help. So I know we're out of time.
Indeed, so maybe you can use it just to flash the topics so that people know a little bit about what will be good discussion topics for discussion in the breakout. Yeah,
I think that's exactly right. That's how I wanted to conclude it, which is again these questions that came up at the beginning, and I think these are key. As people are thinking about integrating the Commons libraries into their own systems, what are the kinds of stores that people are interested in? Because reading and writing out of the library itself is reading and writing out of stores is going to be not just a part of the Commons, but a part of the library itself. That's always the first step in a workflow. How do we deal with identity? Deciding who somebody is, making sure they're who they are, and whether or not they have privilege to the system, and whether they have budget. What are the use cases for distributed versus sort of local or in-memory computation, and then these language choices of Rust for the underlying library through bindings to other languages, and the idea of an API that's unopinionated. Are there other API necessities that other people would want? And we can talk about all of these in the breakout sessions. And if you have questions about these things, please do put them in the Google Doc, and that will help to structure the breakout discussion. But thanks for all the time on this.